David. David is a senior research scientist at Deepmind. His research spans AI, ML, and computational science. He received his PhD from Columbia in 2015, working at the Center for Theoretical Neuroscience. He's been doing a lot of nice work on applying ML to computational physics, and we're excited to hear from him today on deep neural networks for ab initio quantum chemistry.
All right,
Please take
thank
it away.
you very much. All right. So yeah, it's a pleasure to be able to speak here. It seems like a like a great audience, a great mix of people across a lot of backgrounds, and so this will be a talk that combines together things from a lot of different areas. But I'll just dive right in. So the basic idea about this talk is how can we use methods from deep learning to solve the many electron Schrodinger equation. And so why do we care about that? Basically, if you can solve that, you've kind of solved all of chemistry. You can predict from first principles which chemical reactions will happen, but also quite a lot of condensed matter physics as well. It comes down to basically just studying the collective properties of electrons if you want to understand what things are metals or insulators or superconductors, or even more exotic, topological states of matter and things like this. It all just comes down to the collective quantum behavior of electrons, so many electron systems. And even 100 years ago, Paul Dirac nicely summed up the situation when he said, basically, at the level of atoms and molecules and materials, we understand all of the laws of physics and chemistry. Now all we just need to do is solve them. And 100 years later, we're still trying to solve them, and that's still a very difficult problem. And so since then, computational quantum mechanics and quantum chemistry has grown into a whole field of its own. There have been Nobel Prizes awarded in this field, but pretty much all of these methods, there's sort of a whole menagerie of them, and they all have different advantages and disadvantages. So at one extreme, you have methods like Hartree-Fock, which are basically mean field methods, which are very fast and scale cubically in the number of electrons, but are not very accurate. At the other extreme, you have progressively more complicated and more accurate polynomially scaling methods. And at the very, very far extreme, you have what are called full configuration interaction methods, which actually scale factorially, but up to a certain level of discretization are technically exact. Let me see if I can pull up a pointer here. Okay, cool. And basically, for all of these methods, they're just different ways of solving this seemingly simple equation, right? So H here is your Hamiltonian, so linear operator. Psi is the wave function. It's a possibly complex valued function that takes electron positions and, in principle, electron spins as inputs. So each R here is just a three-dimensional vector, one for each electron. And to solve the time-independent version, you want to find eigenfunctions of this operator. And so you have states of constant, so the eigenvalue is the energy, so you have states of constant energy, right? And so all of these methods are basically trying to do variations on this. And you also have density functional methods, which sort of exist in a class of their own, where the idea there is that rather than actually trying to solve for the full wave function, which is a function of all electrons individually, you're actually trying to solve just for the density of electrons. And there's beautiful theory showing that in principle, this can be arbitrarily accurate, but it depends on knowledge of what's called the exchange correlation functional. And though you can show that that exists, there's no real way to compute it. So in practice, you use approximations that are not as accurate as some of these methods. Okay, so what we want to do is we want to make this more accurate with deep learning. And so again, to this audience, you're probably already familiar with most of these, but in the last decade, neural networks have sort of gone from strength to strength. They've shown amazing results in object recognition, for game playing, like beating the game of Go or Atari games, for natural language, like these GPT-3 type language models, where the more data you throw at them, the more sort of uncannily realistic they start to become. So we know that neural networks are fantastic at function approximation, at least if you have enough data. So why not use them for approximating a wave function? And so this is the idea behind a group of methods that are combining one of these methods called quantum Monte Carlo with deep learning. Some people have taken to calling this deep QMC. And so the fermionic neural network that I'll be telling you about today is one method within these class of methods that works quite well. And as I said in the title, this is specifically about ab initio methods. So for those of you who are more familiar with machine learning, what does this really mean? What kind of learning am I talking about here? So in the space of machine learning, there are a lot of analogies between machine learning methods and sort of existing methods in the world of computational chemistry and computational physics. So what gets called empirical methods in computational chemistry pretty much maps onto supervised learning. So most of the time when somebody says they're doing machine learning for quantum physics, they're usually doing something like this, where they use either experimental data or really accurate ab initio data, and maybe train a neural network to fit that data so that you can, say, run things faster or generalize out of domain. The quantum mechanical analog of unsupervised learning would probably be something like quantum tomography, where you don't have any sort of labeled data. You just have a bunch of observations that comes from some quantum system, and you want to reconstruct what the wave function is that generated that. So it's a bit like generative models in machine learning. But what we're talking about, quantum Monte Carlo, is a type of ab initio method. And the best analog I can maybe think of in machine learning is maybe something a bit like self-play and reinforcement learning, where the data is generated by the model itself. So you don't even have training data, really. So there isn't really a term in this for machine learning. I've taken to calling this self-generative learning. So if anybody likes that term and wants to use it, please go ahead. But at least in the computational chemistry world, it's typically called ab initio. So this, I think, distinguishes it from a lot of other work using at the intersection of chemistry and machine learning that's more in the supervised vein. Okay. So then, as I said, how do we actually learn a wave function? What would self-generative or ab initio learning look like? So again, what we're trying to do is find eigenfunctions of this operator, the Hamiltonian, and you can break this up into a kinetic energy term that basically is the Laplacian of the wave function, and then a potential energy term where you have terms for interaction. It's just a 1/r potential, where you have basic electrostatics. You just have electrons and ions interacting. And the convention is to use lowercase r for electron positions and capital R for nuclear positions. So this just gives you the potential energy. So psi squared, you have some constraints on it. Or sorry, psi, the wave function that you're trying to learn, you have some constraints on it. Psi squared should be a probability density function because H is a symmetric operator or a Hermitian operator. Then for psi to be an eigenfunction, it has to be real valued, so we don't have to worry about complex values in this talk. And also for electrons, I'll get to this later, but the thing that makes this complicated is that this has to be anti-symmetric with respect to exchange of electrons. And you can solve this exactly for hydrogen, but nothing else, basically. In continuous space, pretty much nothing else. No real systems, at least. So quantum Monte Carlo is a computational method for solving this. It's considered a fairly, in some ways, a sort of cheap and not very accurate method, at least variational quantum Monte Carlo. The objective function you're trying to solve for is given by, this is basically the Rayleigh quotient. So the minimum of this is going to be the smallest eigenfunction of h hat. And because psi in general, we might not necessarily use a normalized wave function, you have to add this normalization term here. If we expand this out as an integral, it looks like this. And you can see this term here almost looks like a probability distribution. If this were a psi squared rather than a psi, this would be a normalized probability distribution. So what you can do is you can basically write this as an expectation if you pull out psi squared. And so you can write out another way that might be more familiar to a machine learning audience to write this objective function is like this, where P is a probability distribution proportional to psi squared. We have to put in this psi inverse because the squared is missing here. And this is a term that's called the local energy. And that's basically called that because if psi is actually an eigenfunction, then the psi and the psi inverse will cancel out, and this will just be a constant everywhere that's equal to the energy. So basically what makes it quantum Monte Carlo is that you evaluate this expectation using Monte Carlo methods to sample from psi squared. Okay, and this was originally this was not actually minimized. You would just plug in a fixed functional form for psi and just evaluate these integrals. So this is used in the study of liquid helium originally, was extended to fermions in the 70s. And there are basically two main types of quantum Monte Carlo. One called variational quantum Monte Carlo, where you directly minimize this. This was called variational quantum Monte Carlo because this is an upper bound on the ground state energy. So even if psi doesn't give you an exact solution, you know it's at least an upper bound. So that gives you a way of comparing different methods and evaluating which one's better. And diffusion quantum Monte Carlo, which actually is very, very closely related to sequential Monte Carlo or particle filtering in machine learning. It's basically the same idea with a few extra tricks, where you have a set of particles undergoing diffusion, and you update some weights on these particles, and you also do a sort of birth-death thing to make sure that the weights don't get too skewed on the particles. So diffusion quantum Monte Carlo is generally much more accurate, but it's also more difficult to do things like evaluate forces, while variational quantum Monte Carlo historically has been thought of as a sort of cheap but low accuracy method. But what we found is that by using deep learning, we can make this as accurate as many of these much more computationally demanding and much more complicated methods. Okay. And so when I say accurate, or not so accurate, in computational chemistry, the standard level of accuracy that people go for is usually what's called chemical accuracy, or about 1 kilocalorie per mole. And just for some context, as I said, these Hartree-Fock methods are a type of mean field method. Those will usually capture about 99.5% of the energy in a chemical system. The leftover 0.5% of energy is what's called the correlation energy, and chemical accuracy, depending on the system, will typically be in the range of 99% of the correlation energy. So for a system that has in what are called atomic units, the unit of energy is Hartrees. And so for a small, say, hydrocarbon system, the total energy might be 100, 200 Hartrees, but the energy in the bonds will be on the order of thousandths of a Hartree, of the order of millihartrees. So this is really an exceedingly high standard of accuracy, especially compared to the kind of things that, if you get 87% top one accuracy on ImageNet, you have the best object recognition system in the world. But here you need, 99.9995% accuracy. Okay. Is everyone following so far? I feel like on these talks, it's sort of hard to gauge if people are following along, but if anybody has any questions, just jump in. Can everybody hear me?
Yeah, I can hear you.
Okay, great. So that's the objective function that we're trying to minimize. But I mentioned that you have to, directly optimize psi. How do we actually represent psi? So as I said, what distinguishes fermionic wave functions or wave functions for electrons from other systems is that it has to be anti-symmetric. You exchange the position of two electrons and you get a minus sign. So what this means is that if you have two electrons with the same state, the wave function will be 0. The probability of finding that configuration is 0. So two electrons can never have the same configuration. This is the Pauli exclusion principle. Okay, so one very natural way of representing an anti-symmetric function is to use determinants, because determinants have the nice property that they're anti-symmetric under exchange of rows and exchange of columns. And in fact, I think they're the only function or the most general function that is multilinear and anti-symmetric, or there's some way of formulating things where you can show that the determinant is the most general anti-symmetric function that has a certain property. So there are natural reasons that you want to work with these. And it's also just kind of a mathematical miracle in some sense that determinants can be computed in cubic time. Whereas, The equivalent for symmetric functions, the permanent, can only be computed in factorial time. So in some ways, it's actually much harder to deal with bosonic systems than fermionic systems. And so the starting point for most of these wave functions are what's called the Slater determinant, where you have a set of functions that are a function of single electrons. So each of these functions is not a function of all electrons. It's just a function that maps, a point in three-dimensional space to a scalar, and you construct a matrix where each row is one function and each column is one electron, and the determinant is known as a Slater determinant. So the minimum energy solution for if you represent your wave function as a Slater determinant is known as the Hartree-Fock solution. So it's equivalent to mean field methods in statistical physics in many ways. But then there are certain things that are very hard to represent in this representation. For instance, electron-electron correlations are hard to encode because these are a function of single electrons. So you can include a multiplicative factor that has basically a term for every pair of electrons. And so this is just a rotationally symmetric scalar term for every pair of electrons. You multiply them all together, and it's still an anti-symmetric function. And this is what's called the Jastrow factor. And you can also, so this sort of changes things after the Slater determinant. You can also add correlations between electrons before they go into the Slater determinant. So you can do a coordinate transform called the backflow transform, where you take another scalar function, rotationally symmetric function of electron positions, just add up all of them for every other electron, add it to this electron position, and use this new transformed coordinate as the input to the Slater determinants. This actually was originally developed by Feynman and Cohen for studying superfluid helium. But when you put all these terms together, and you can also take a large linear combination of many of these determinants. So putting these all together and plugging this into this variational quantum Monte Carlo, you get the sort of standard Slater-Jastrow backflow function. And this is like the go-to off-the-shelf method that everybody in variational QMC uses. There are also fancier things called using what are called geminals and Pfaffians that have some advantages. And so there, instead of functions of a single electron, you can plug in functions of 2 electrons, but the performance you get is sort of in the same ballpark. So this is kind of the baseline that we're comparing against. And so the idea is that rather than this fairly restricted wave function form, can we actually write down a neural network that generalizes this, and that's much more expressive than this, and therefore can be expressed much more compactly? Because in theory, if you have a large enough linear combination of Slater determinants, if you have enough of these coefficients omega k, you will eventually get a universal representation for anti-symmetric functions. But as I mentioned, the case where you do a sort of arbitrarily large linear combination, then you arrive at full configuration interaction, and that scales factorially. And often you'll need hundreds of thousands or millions of these determinants with these Slater-Jastrow functions to get good performance. So it might seem like a neural network is in some ways more complicated, might have a lot more parameters. But if you want to actually make this accurate, just the number of weights that you need here can go into the millions. So it actually can be a huge, huge number of parameters. So as we know from a lot of machine learning, replacing a big linear combination of things with a nonlinear function approximation can often work a lot better. Okay. So now we have to build an anti-symmetric neural network. And that's kind of an unusual constraint. A lot of work has gone into designing neural networks with things like permutation equivariance, translation equivariance, or invariance. Spherical equivariance is, I guess Max is at this meeting, so he knows all about that. In fact, I believe Taco spoke at one of these specifically about that. So the fermionic neural network is specifically a neural network that is meant to be anti-symmetric. And so how do we build that in a neural network? So the key idea is that we want to take these orbitals that we're plugging into these determinants, these functions of a single electron or maybe a transformed coordinate of a single electron, and generalize it so it becomes a function of all electron positions. Because the resulting determinant will still be antisymmetric as long as the orbitals are symmetric in every input except one. So you want the inputs to be permutation equivariant. You basically put in n electron positions as input, and you want to make it so that if you swap any two of these electrons, the output will still be, the two outputs will be swapped. And then you can take those output vectors, pack them into matrices, and take the determinants. Okay, so then we have to say, all right, how do we represent a permutation equivariant function? And so you can start with just a sort of standard neural network, one for every single electron. And so this is basically just a neural networky way of representing like Hartree-Fock. If you pack these all into a determinant, each of these phi's will just be a function of one electron. So that's not doing anything novel or interesting. But you can also add some kind of permutation equivariant interaction between all of these layers. And so at each layer, we can take the activation at one layer, sum all of them together, and then concatenate those in as an input to the next layer. And so this is actually an old idea for how to build equivariants, permutation equivariants into neural networks. I think it dates back to John Shaw Taylor in like the late 80s or early 90s. And using this to represent antisymmetric functions, adding this determinant at the end, although it's very simple, it is in theory universal. So Marcus Hutter had a nice paper showing that, following our paper on the Fermi net. In practice, you need to make a few extensions, even though in theory it's universal. In practice, you have to add a few extensions to get good behavior. And so at the moment, a bit like these Jastrow factors, we need some way, or we found that adding in some way to represent correlation between pairs of electrons improves performance a lot. And so we actually add in a second stream to the network, where it's basically for every pair of electrons, we have just a single MLP all running in parallel. And then we basically sum up the activations for one of these rows and concatenate those in as well as sort of a second set of features going in at every layer. And so that encodes features of pairs of electrons and allows you to capture things with electron correlation that's very difficult to do with this first part of the network. And we also find that a single determinant isn't quite enough, but a pretty small sum of determinants, like a few dozen, rather than tens of thousands, is good enough to get very good behavior.
Sorry, can I ask a question on this?
Yes, absolutely.
So how about, so in graph neural networks, you would also include the adjacency matrix in some sense, right? And when you're looking at the, could you do something similar here that you kind of?
You definitely could. The systems we've looked at are only going up to maybe a few dozen electrons, and they tend to be all pretty close to each other. So basically, you can think of this as sort of like a graph neural network that's just all-to-all. But I think for larger systems where you have a lot of sort of distant electrons that aren't likely to be interacting with one another, so if we're scaling this to hundreds or thousands, that's exactly what we'd want to do, is some kind of more sparse graph neural network type thing. Yeah, so that's interesting future work.
Thanks.
Hello, I also have a question.
Yeah.
So here you have the wave function. Does that mean every time you do backpropagation, you have to sample once from this wave function? So
yes.
The square of this wave function. Okay, so that's very time consuming. But
that's not the most time consuming step, because basically to update the samples that you're putting into this network, we don't, because we're only changing the network a little bit every step, we're not running the MCMC chain like all the way to equilibrium. So we tend to just do a few steps, and so it just needs a few network evaluations. The real limiting step is actually evaluating the kinetic energy operator, because there you need to evaluate the Laplacian with respect to the inputs. So that means you need to evaluate, it basically has the same cost as evaluating the Hessian of the network.
Right, but what you're talking about is that you are taking the second derivative of this, but you're doing that numerically, or you're doing that using some autograd stuff?
We're doing that with automatic differentiation.
Okay, cool. Okay, thank you.
But yeah, in practice, like something like 90% of one iteration is, especially for larger systems, is going to be the kinetic energy evaluation. Okay, so yeah, so implementation details. I hope this loads. There's a nice animated GIF that should pop up here, but it's, I probably should downsample that. But yeah, we're not doing anything very fancy on the MCMC side. It's just conventional Metropolis Hastings. Sometimes for larger systems, we're doing essentially Gibbs sampling, or what they call one electron moves. Here it is. So you can actually see the particles, or what they call walkers. This is for a nitrogen molecule. And yeah, so for larger systems, Gibbs sampling can be helpful. We tried fancier methods. We tried, HMC and other gradient-based methods, but found that oftentimes what happened was you'd make a proposal very far away, it would get rejected, the network will get updated, and what was a good region becomes basically a sort of bad low probability region. And it's actually harder for HMC to escape that than MCMC. And so you would get like huge spikes in your energy, and it would sort of, you have an interaction between optimization and sampling here. So you're not just trying to sample from a fixed objective, but you're sampling, updating your network, and those interact in sort of complicated ways that can sometimes lead to pathological behavior. And I haven't seen a lot of research on sort of the interaction between sampling and optimization. I've seen some on sort of 2 time scale optimization, so where you have 2 coupled optimization problems, but not a lot on a coupled optimization and sampling problem. So I wonder if there are sort of theoretical advances that could be made there that might be useful for this. Sometimes people will do things like use heuristics, like things called space warp coordinates, where they'll try to change the position of the walkers in a way that conforms with how the network is changing. But those are more sort of heuristic. So that's one implementation detail that you have to get right. Another is that the optimization, because we need to get really, really high accuracy, and we're less worried about generalization than we are about asymptotic performance. So that's a little different from most of machine learning, where if you under-optimize things a little bit, it's actually good. You're more likely to get good generalization. Here, we actually really want to optimize things to the bone. So we use an approximation to natural gradient descent called Kronecker factored approximate curvature, or KFAC. So this works very well with neural networks, because you basically assume that your Fisher information matrix has this block diagonal structure, and that the blocks themselves have this Kronecker factorized structure that matches the structure of the neural network. And we just find that you get, when you cut the error by an order of magnitude, even on small systems. This is just showing optimization on a log-log scale for single atoms, so just lithium up to neon. And the larger the system gets, the larger the improvement gets. And we're not really sure why there's this big discrepancy. I think some of it is that the Ferminet is sort of an unusual architecture, so a lot of networks like ResNets and things like this are kind of designed to work well with Atom, and we're designing our network to work well at representing a wave function. So these sort of approximate second order methods might be, the model itself might be sort of ill-conditioned, and so these approximate second order methods don't struggle with that as much. But yeah, in a lot of machine learning, KFAC has gotten a reputation for being very fancy, but doesn't give you much of an advantage. But on this application, at least, we find a huge advantage. As the other thing is that there's as I said, there are a lot of kind of connections between these fields. you could almost write a glossary kind of going from machine learning terminology to computational chemistry terminology and computational like quantum Monte Carlo terminology. And in the electronic structure community, the stochastic reconfiguration method is almost exactly the same as natural gradient descent, or at least you end up with the same algorithm. There are some things that you can do in the quantum setting if you're looking at, say, time evolution of a system, and so this matrix then becomes complex. So in some sense, it's actually more general than just natural gradient descent. But there's a really beautiful mathematical connection between these fields. So that's how we implemented it. And how well does it do? So getting to these results. So we wanted to look at a really apples to apples comparison against these Slater-Jastrow backflow networks. And so that involved looking at things with the exact same number of determinants, so that things should be, in some sense, equally expressive. So there's very good benchmark data for single atoms from this paper from a decade ago. First of all, typically these orbitals are represented by discretizing the space, by picking something a bit like a Fourier basis or like spherical harmonics to represent functions in R3. And that's called the basis set. And so just by using a neural network in place of, rather than a basis set, we can already get some improvement in the energy. But we find using the Ferminet, we cut this error dramatically. And the gray area here is, that's chemical accuracy, the standard of 1 kilocalorie per mole I mentioned. So one determinant isn't quite enough to get chemical accuracy, but it's far more accurate than a Slater-Jastrow wave function. If we start adding determinants, so this is now for a larger system. So this is carbon monoxide and the nitrogen molecule. So we're looking at systems with about 14 electrons here. You can see that this Slater-Jastrow network gets more and more accurate as you add more determinants. But it also gets a lot harder to optimize, which is why you see a bit of a bump here is actually difficulty in optimization. So you should see this as an upper bound. But the performance of the Ferminet, is always better, and basically gets down almost to chemical accuracy just with a few dozen rather than tens of thousands or hundreds of thousands of determinants. And it's also substantially easier to optimize. These optimization difficulties that we had here were totally absent with the Ferminet. The Ferminet gave you, pretty identical results every time.
Can I ask a question about what exactly you're optimizing?
Yeah, sure.
So I understand that based on the cost function that you're looking at, you're finding states that are closer and closer in energy to the true ground state.
Yeah.
You have a similar sense of whether they actually look anything like the true ground state, because
yeah,
situations where you have a highly degenerate ground space and the true ground state is, or almost degenerate ground space where the true ground state looks very different from some low energy state.
Yeah, I think the systems like that, I think that's often what is referred to as like multi-configurational, and typically you need a lot of determinants to represent them. We've found, like the nitrogen dimer when you're sort of in the bond breaking region, because that's a very complicated bond. You have sort of 3 electrons from each atom, and in that region, you sort of got these 2 states, one that looks a lot like 2 isolated atoms and one that looks like 2 bonded atoms very close together. We find the energies are quite good in that region, and I think I have slides somewhere in there. We've looked in some systems at things like the energy density and even the exchange correlation holes. So basically looking at the difference between the energy density on average and the energy density conditional on another electron being nearby. And you do see like exactly the kind of holes that you expect. The electron densities for the hydrogen chain look reasonable. But of course, there's always the question of like, well, what's the ground truth that you're comparing against? So if you have any ideas of systems that would be useful to look at, we're always open.
If you run this on the hydrogen atom, for which you have an analytical solution to what the form
Yeah.
and you
Well,
calculate.
so this is just for ground states. I've sort of run similar. I ran a similar method that we were calling spectral inference networks, where you're not actually sampling from psi squared, but you can get excited states. But because you have to do you're not getting unbiased gradients in that case, so the optimization is very, very, very tricky. It's very, very delicate, and so it was a lot more difficult to scale. But what we found there was for like p orbitals, you would get 3 orthogonal p orbitals, but they would sort of rotate over the course of optimization. So they would sort of you would get sort of an arbitrary, as you said, they're degenerate, so you would get like an arbitrary rotation because there's nothing in the loss function that you're minimizing that picks a certain rotation over the other. So if it's degenerate, it'll just sort of arbitrarily pick one of them.
Yeah, I guess what I'm suggesting is in situations where you independently have an analytical form for the ground state, you can calculate these various overlap or state fidelity kind of functions.
Yeah, I think you would, if you have for anything we're looking at, you wouldn't really have an analytical solution. You would have sort of other computational solutions. So you might be able to get like a solution in a particular basis set. So maybe you could try comparing it against that. Though I think, what we've been using as the sort of ground truth reference for a lot of these has been coupled cluster methods, which work well for equilibrium systems. But I think you don't actually get an explicit ansatz out. I think the wave function ends up being represented implicitly. I'm less of an expert on coupled cluster there.
Mm-hmm. Yeah,
but yes, maybe for like some of these model spin systems, like Heisenberg systems and stuff like that, you could get analytical solutions. But part of the reason we're doing this is we're interested in solutions where there are no analytical methods.
Yeah, I guess it's just a little unclear whether you'll actually get the true ground state, if that's the specific thing that you want, if there are degeneracies that you don't know about.
Yeah, I think, what you see there is that, well, N2 is also a good system for this because, I don't have the figures in here, but we've been looking a little at spin states. And so there is actually kind of a transition where the ground state goes from having 0 spin magnitude to a non-zero spin magnitude. And you do see the energies are like the area where it struggles the most, where the energies are highest relative to, that's small enough that you can do something like full configuration interaction. And what you see is that specifically where that transition happens is also where the errors are the biggest, but the errors are still on the order of 5 or 10 millihartries. So it's still pretty accurate. It's still better than coupled cluster. Okay, so I'll try to get through some of these results in the time that we have. So as I said, for ground state atoms, we do a lot better. And in fact, so diffusion Monte Carlo, which I said was it's pretty much always more accurate than variational Monte Carlo if you do it right, is in red here. This is variational Monte Carlo using the standard Slater Jastrow backflow wave functions. And this is the Fermionic here. And since these are small systems, you can also do these exact these really, really accurate exact methods. Coupled cluster, because it's not actually variational, actually overshoots on some of these systems. But we're getting it pretty much smack on. So better than diffusion Monte Carlo on many systems, which was surprising to us, and I think was surprising to many people. We can also generalize this to bigger molecules. So as I said, the correlation, the level of accuracy that we're looking for is this tiny fraction of the total energy. And looking at these molecules from lithium hydride, which is just 4 atoms, up to bicyclobutane, which is like 30 atoms, we do get some degradation in performance. We're using coupled cluster as the baseline here because these systems are just too big to do exact calculations. So we get better than 99% of correlation up to some pretty big systems. And even bicyclobutane is still, I would say, impressively good for a system that big. And the results we're comparing against, we're actually doing some extrapolation. So this is comparing the error to the extrapolated results. But these are the different unextrapolated coupled cluster methods. At a certain point, these systems get so big that the most accurate ones just run out of memory, whereas we use networks of a fixed size. And so we're more accurate than coupled cluster in a fixed basis set, basically. And so we think that if we were to use sort of bigger and bigger networks and do a similar extrapolation, we think that we would also find results this good. But this is still impressively accurate. And in some sense, because we're comparing different computational methods to one another, it's not always clear what the standard of accuracy is. It's not clear what the ground truth is. So what you really want to do is compare against really accurate experimental results. So on this system, this largest system, bicyclobutane that we've looked at with 30 electrons, the transition from bicyclobutane to butadiene has multiple possible conformations. What are called the conrotatory and disrotatory pathways. And this is also a system that coupled cluster struggles with. It predicts, I believe, that the disrotatory pathway is the lower energy and preferred pathway, while actually experiments show that the conrotatory pathway is the true solution. So just comparing the difference in the Fermi net energy for the different systems and comparing against very accurate diffusion Monte Carlo computations, which are consistent with other even more sophisticated coupled cluster methods, we do find that for all of the different transition states, we get basically within chemical accuracy of these other methods. So this worked pretty much out of the box. We didn't have to do any sort of fancy tuning, which is often very rare for some of these fancier quantum chemistry methods. So this is really encouraging results that even on bicyclobutane, where we don't know how much to trust the absolute energy, the relative energy seems to really nail it. Okay, and we've also looked at some of these benchmark systems like the hydrogen chain, which is a really good benchmark system because there was this paper just with 1 million authors on it where they compared every kitchen sink computational electronic structure method. And so this is one of these exact methods as the baseline. Just looking at the energy curve, they're all so close that you can't even see it without zooming in. Standard variational Monte Carlo is here in yellow, but the Fermi net is in light blue. Is again much more accurate. And looking at network ablations, we can get a sense of what's actually working for these networks. So adding layers helps up to a point, but actually past 3 or 4 layers, it doesn't make a huge difference. Adding more units to this 2-electron part of the network, it's part of the network meant to capture electron correlation, helps up to a bit, but again, it tops out with pretty small layers. Like you only need about 32 units to get things pretty accurate. Where you see the biggest improvement is in making the layers wider, not deeper, which surprised us in the 1-electron part of the network. And there you see sort of an exponentially decreasing errors as you make things wider. Okay, and as I said, there's sort of this burgeoning field of deep QMC. A lot of ideas bouncing around about how to combine deep learning and quantum Monte Carlo methods, how to do ab initio calculations, self-generative calculations. And sort of around the same time that our paper came out, another method called the Pauli net was published. That was using, I think this SCHNet or SCHNet is one of these equivariant neural networks or permutation equivariant neural networks or graph neural networks developed originally, I think, originally for potential energy surfaces, but you can use it also to do the same idea that we said of constructing permutation equivariant inputs to the determinants. Their networks are a little smaller. So I think the biggest difference is basically that their networks are smaller, so they train faster, but are less accurate in terms of overall energy. So this is looking at the cyclobutadiene, which has two different configurations that it'll sort of oscillate between. And in terms of absolute energy, the Ferminet gets something like 40, 50 millihartries lower. Looking at the relative energies between the rectangular and the square state, we get pretty similar results. And these results are all basically at the high end of the experimental range. And again, this is yet another system that coupled cluster struggles with, because anything that's sort of away from the ground state, anything that's stretched, CCSDT is not very good at. But these multi-reference coupled cluster methods tend to work much better for. And so we're pretty much in agreement with all of them. And again, this works pretty much out of the box. Or they both work pretty much out of the box. So there's sort of a whole class of models like these. Neural network backflow was maybe one of the first, but that was exclusively for discrete systems. So they looked at Hubbard models and things like that. We were one of the first for continuous systems. There was a method called DeepWF that did not use determinants. It used something that scaled quadratically rather than cubically, but the results were just not very accurate. So we were also one of the first methods to reach better accuracy than Hartree-Fock. So Hartree-Fock is kind of, table stakes in quantum chemistry. If you can't do better than Hartree-Fock, there isn't much of a point. So we were one of the first to show that. And there was another paper that came out around the same time as ours in the PauliNet that rather than representing things in first quantization, where you have positions of the electrons as input, they represent things in second quantization, where you're actually counting the occupancy of different states. So that's sort of an interesting alternative approach. And there's a lot of active work in that direction as well. And I think there was even a recent paper on something called Deep Irwin. That's yet another one of these methods that's also sort of a small low accuracy method, a bit like the PauliNet. So this is I'm not going to say exploding field, but there's a lot of work in this field. And so we hope that sort of newer, more advanced architectures will come along that will do even better than the Ferminet. So to wrap up, I guess I'm pretty much out of time. So we've designed a new type of neural network that is anti-symmetric with respect to its inputs, specifically to use as a way of representing wave functions. Combining that with powerful approximate second order optimization is a really effective strategy and gets, especially for using deep learning, incredibly accurate results. Scientifically, levels of accuracy that are good enough for scientific computation. There's some difficulties with interaction between optimization and sampling that I think are actually counterintuitive. But we've actually shown that this fairly cheap and less accurate variational quantum Monte Carlo method can be made competitive with, and in some cases even better than, things that are typically considered the gold standard for all electron calculations. But there are a lot more things to do in terms of scaling to bigger systems, adding in periodic boundary conditions if you want to extend this to condensed matter physics. There you have to treat, systems which have periodic boundary conditions. We'd like to extend this to heavier atoms. I sort of breezed through this, but we've actually got really accurate results all the way up to argon now. So all the way up to electrons with 18, all the way up to atoms with 18 electrons, atomic weight 18. But getting beyond that into things like transition metals becomes a lot harder, and just lots of room for improving the optimization and things like that. So that, I want to wrap up and say, thank you to my collaborators. And this was actually a real joint collaboration between sort of machine learning people and quantum chemistry people. So James Spencer and I have, worked together on this from the very start. He comes from a quantum chemistry background, and I come from a machine learning background. And Matthew Folks at Imperial College was very kind to advise us on many of the finer points of quantum Monte Carlo. And the papers are up online, and the code is online as well, including a new version in JAX. So please take this, play with it, take it for a spin, find bugs in it, give us pull requests. And if you have any more questions, don't hesitate to get in touch. Thank you.
Thank you very much for the very nice talk, David. Questions?
Hello, I have a question.
Mm-hmm.
So is the Jastrow factor necessary in your Ferminet?
So we don't have a Jastrow factor in the Ferminet. What we have is this part of the network.
Oh, you have like, yeah. Go ahead,
yeah, so we have, we have this part of the network that takes pairs of electrons as input. And so that's sort of like a generalized combination of backflow and Jastrow factor. But yeah, so one of the things that Jastrow factors are really good at is capturing what are called the cusp conditions. And that's what happens when basically two electrons overlap, or an electron and a nucleus overlaps. And then you have a divergence in the potential energy. The potential energy goes to infinity. And what that means for what you can show is analytically, the ground state wave function, it has to be non-smooth there. So it's well defined, but the derivative isn't defined. And we found that all you have to do is actually put the absolute value of the distance between electrons in as an input, and then that gives you a function that is non-smooth at the cusp as an input feature to the network. So the network itself is smooth, but the inputs are a non-smooth function of the electron positions. And that is enough for the network to learn the cusp conditions. But if you don't include that, the energy is way off. It really struggles.
So in your network, the term is like exponential minus the distance. So that term is very important in your structure.
Yeah. So we don't put in an exponential. We just put in the absolute value of the distance, but we probably could put in some monotonic function of that, but we sort of let the network itself learn what that monotonic function is.
And you're saying that even you have that kind of like a gestural style thing, your HMC still fails? HMC still doesn't work?
Yeah, HMC just really struggles. I don't think it's because of the cusps. We thought it might be like going crazy when it goes near the nucleus. But we're not doing HMC on the potential energy.
Okay.
We're doing HMC on psi squared. And psi squared is pretty well behaved. So the problem is how it interacts with the optimization. It's basically because it'll make a faraway step, the step gets rejected. And I think if you're using Metropolis Hastings, it makes lots of little steps. So it might not mix as fast, but it's less likely to get stuck. Something like that. So probably with more work, we could fix that. But Metropolis Hastings seems to work well enough that it's not killing us. It doesn't seem like the limiting factor.
Okay, thank you.
Mm-hmm.
All right, so I have a question on why you think that this is like doing a better job than the Jastrow factor. So like, it seems like with machine learning, you're getting some kind of nonlinear approximation or something like that. Like you're using like it's almost like you're getting a low rank approximation of the solution, which you're able to represent in the fewer determinants. So if the Hamiltonian is linear, why are you getting that to happen?
I feel like there were a few different questions there. I mean, the Hamiltonian is linear, but it's a linear operator on a very high dimensional function. So it's still a very, very big space of, it's an infinite dimensional space, but it's a big Hilbert space of things that you're trying to find a solution in. So you want to build in as much as you know about the solution as possible. And so like the Pauli net builds in the cusp conditions, whereas we learn them. So we build in the non-smoothness of the cusps, but we don't build in what the actual like slope of the cusps is. I mean, just empirically, we see, I think we've played around a little bit with building in exact cusp conditions. We haven't really gotten it to work very well. But again, I think that's just a matter of not putting in as much effort, because empirically, it seems like it learns them fairly quickly. And so it seems like there's just other stuff that takes much longer to learn, that so much so that this doesn't seem like the limiting step.
Okay,
But I don't,
so
yeah.
it's the finding psi that's the okay.
Yeah, it's like, you know, one thing with the cusp condition about the shape of psi in, you know, a set of points of measure 0, basically. But, you know, what psi looks like in the entire rest of the input space, you don't know.
Okay, got it.
Yeah. But yeah, I think an exact cusp version of the Fermionic probably would work. It's just a question of finding the time to do it.
I have a question.
Yeah, go ahead.
Yeah, could you talk about the computational performance of Ferminet? So as far as I understand, the network is growing with the number of electrons.
Yeah.
So how does the computational performance scale, and how could you also mention like the scaling bottlenecks of the code? You mentioned calculating the kinetic terms, but could you give more details about the computational terms that are costly?
Sure, yeah. So the network does grow. So you can have a network with a fixed number of parameters. And there's a question of how many parameters do you need to reach a certain level of accuracy, but let's just set that aside and say for a fixed number of parameters, the overhead in terms of space will grow linearly. Or sorry, no, actually, for one part of the network will grow linearly, but for another part will grow quadratically, because the number of pairs of electrons grows quadratically. So overall, the space requirements grow quadratically. Evaluating a forward pass grows cubically because the determinant actually is a cubic function. At the moment, we're dealing with small enough systems but that isn't really the bottleneck in practice. The constant factor from other stuff tends to be bigger. But in a certain, you know, as things become big enough, the determinant computation will dominate. There's another reason you might want to do something graph nutty for bigger systems, because then you could do like sparse determinants. Then in terms of actually computing an update step, the KFAC will scale cubically in the width of the layers because you have to invert a matrix that's the size of the width of the layers. But again, that's not the bottleneck. The real bottleneck is this kinetic energy computation, because then basically computing a second derivative has like 4 times the cost of doing a forward pass, because you basically do a grad of a grad. And then you have to do that n times. You have to do that for every direction, or 3n times. You have to do that for every direction in space. So if a forward evaluation scales as n cubed, computing the kinetic energy will scale as n to the 4th. So that really dominates, which is why you will need to do some kind of sparse thing to scale to truly large systems. In practice, what that means is, like for these biggest systems I showed, like the 30 electron systems, like bicyclobutane and butadiene, we're talking like 8 V100 GPUs, maybe running for a few days. So it's not cheap. But you know, if you go on some of these like big UK national supercomputers and look at what they're actually spending most of their compute time on, it's basically either fluid dynamics or computational electronic structure stuff. So people are certainly burning lots of compute cycles with these other methods as well.
Okay, thank you.
I think we have a few text questions. Have you done anyone to benchmark with diffusion QMC results? We're looking at that a little bit. There was a paper recently from Max Wilson that looked at diffusion QMC on some very small systems, like first row atoms. And I think they were maybe able to get an improvement of, well, you should look up the paper yourself because I might be misrepresenting this, but I think they got a very small improvement of maybe like a millihartry or a fraction of that. Because on the really small systems, as I said, comparing against the exact methods, we're almost nailing them. It's a fraction of a millihartry. It's more the larger systems that are interesting. I hope that answers your question. Can you compute forces on the nuclei? So the forces on the nuclei, you mean like if you change the geometry of the system, if you like stretch it, what are the forces? Like moving the nuclei around? Where does enter? Yeah. In theory, yeah, there's the the Feynman-Hellman theorem says that you can do it at an equilibrium. In practice, there are some error terms if you're not exactly at the equilibrium. So to get accurate results, you typically have to include those error terms as well. One of the really nice things about this is like computing forces in diffusion quantum Monte Carlo is really hard. But there are ways to do it in variational quantum Monte Carlo. So you can do it with the Fermionic the same as you could do it with a Slater-Jastrow ansatz. So this is we haven't published anything with that, but you can do it the same as you can with any other VMC method. So yes.
Yeah, I actually have a question on this K-fact.
Mm-hmm.
So yeah, have you actually compared the result from K-fact to this natural gradient descent or stochastic configuration?
Mm-hmm.
So yeah, have you compared the results between
compared
two?
It? So numerically, the only real difference between KFAC and stochastic reconfiguration is that there's a normalization term.
Yeah, yeah. But what I was asking is that the difference between KFAC and yeah.
Oh, you mean if I wasn't using the approximation, if I was doing the full thing?
Yeah, then how much it would be accurate?
Well, that's not practical to do on a network of this size because we're talking about hundreds of thousands of parameters.
Yeah, sure.
So we actually can't do exact stochastic reconfiguration. And I guess in principle you could try KFAC on like a very, very small neural network that has only a few parameters, but we haven't done that. And also, if you're looking at a tiny neural network, you sort of know tiny neural networks don't work that well anyway.
Yeah, sure.
So.
Okay. Yeah, another question is that about how many samples actually it actually consumes to be trained. How
many samples? So we typically we're using batch sizes of a few thousand walkers. And so I think all the results I showed is with 4,096. And we typically run it for a few 100,000 iterations.
100,000. That's actually pretty huge.
Mm-hmm. Yeah, I know. Typically, I think in VMC, they'll really go for trying to get exact gradients. So you'll run the sampler for hundreds of thousands of steps,
okay,
and then do one. So you'll only do like maybe 100 parameter updates. But we wanted to do something a bit more like sort of best practice in deep learning. There's lots and lots of little steps instead of a few really big steps.
Okay, so what you mean is that large batch size actually should be used.
Yeah, large batch sizes do make a difference also, yeah, that helps.
Is there any reason why do you think this is the case?
Large batch sizes? Some of it I think comes down to actually the derivatives, getting less noisy derivatives.
Mm-hmm.
So when you compute the derivatives, there's a term that's basically the difference between the local energy and the expected energy. And the way you compute the expected energy is just by averaging over a batch. So you'll get less noisy estimates of the expected energy if you use bigger batches. So you'll get less noisy gradients. That's my guess.
Yeah, but in usual machine learning things, what people do is that actually large batch size leads poor generalization, and they want to avoid such a case.
But we don't really need to worry about generalization in the same way because we're doing self-generative learning. Okay. So we can just generate more samples. So that's less of an issue for us.
Thank you.
You're welcome. I think there's would int psi delta psi was int nabla psi squared. Oh, is it saying would it be easier if we were using a normalized wave function? Is that what the question is? From David Holtzmuller. Not sure I get the question. Or int nabla. Or is this about the derivatives? Sorry, I think you're muted, David. To remove the second order derivatives. For computing forces. I'd have to go through the math a little bit more about. Or do you mean for optimization? Anyway, I'd have to. Oh yeah. I'm not sure how that would work. I mean, we have a fairly complicated neural network wave function, so I don't know how you could write down a form of the wave function where you could use. Or are you saying using finite differences to compute the Laplacian instead of doing it with autograd? So I think if we tried finite differences, it wouldn't be accurate enough. We'd see big numerical errors, and it would end up having about the same cost anyway, because you'd have to do about the same number of using integral equality. Oh. So I think that integral equality does get, when we're computing the derivatives, there is a term that we can remove thanks to that integral equality. But I don't think you can. You still end up having local energies somewhere in the derivative. I don't think you can get rid of them entirely. I'd be happy to go through the math on the derivatives in more detail. Or we have an expression for the derivatives in the paper. Offline if you want. But yeah, oh yes, David Berman.
Yeah, hi. I was interested by your comment about putting in periodic boundary conditions. So I guess you could do things like metals and get Bloch waves if you did that.
In principle, yeah.
Is it difficult? Because it seems like it'd be a relatively easy thing to do. What's the obstruction? I guess I'm asking.
There are some things like making sure the input conditions are correct. You have to, when you're computing the potential energy, you have to do things like what are called Ewald sums. I think when you start looking at like Bloch waves, you have to start worrying about complex wave functions again, things like that.
Yeah.
So there are a few details, but it's not like you'd have to totally go back to scratch.
I just got one other sort of perhaps more general question. You set this up with anti-symmetry because you wanted to mimic electrons.
Mm-hmm.
Are there any other problems that you've thought of, some general problem where you want an anti-symmetric neural net?
Well, what other fermions are there? That's one case. The only case I've been able to think of, and I've not really been able to get the people who work on this interested in it, which I think is a shame, is game theory. Is because there you have, if you have an n, basically you have a value function, and for a two-player game, if it's a zero-sum game, the value of one player's position is the negative of the other player's position. And so in the generalization to an n-player game is that the value a zero-sum n-player game would have an anti-symmetric value function.
Yeah.
There's all sorts of interesting stuff there. But I think, so there's some people in like multi-agent reinforcement learning who are interested in this stuff, but they tend to do things a bit more like this deep WF wave function where you just have pairwise terms and take a product of pairwise terms. And I think that's what they've done. But that's the only other case I've been able to think of where this might be useful.
Yeah, okay, thanks.
You're welcome. All right. Is that everything?
I think so. Thanks again for a super interesting talk.
Thank you for having me.
I think we'll end there. Yeah.
Okay,
Thanks a lot,
great.
David. That was great.
Thank you.